So, good morning, students. Today's lecture will be on pattern of Bussy reaction, which is nothing but photocycloaddition reaction. So, it is a reaction between carbonyl compound and alkene under photochemical condition to give oxytane. Oxytane means cyclic fourth member ring. So, what is pattern of Bussy reaction? Actually, Italian scientist Emanuele Paterno and Swiss scientist George Bussy performed experiment by taking carbonyl compound and alkene under photochemical condition, and the product formation was oxytane. So oxytane means cyclic fourth member ring where one of the carbon is replaced by oxygen. So in fact, this is one of the first photocycloaddition reactions. Now here in the example, benzopenone is treated with isobutene in the presence of light to give oxytane. So the oxytane obtained here is very high, 90% air. So this particular reaction was performed by Paterno and Bussy. Therefore, this reaction is known as Paterno-Bussy reaction. Now here, this Paterno-Bussy reaction can be studied under two categories, depending upon the nature of the alkene. So the alkene we may select electron-rich alkene, or we may take electron-deficient alkenes. So depending upon the nature of the alkene, the product formation will be different. So first of all we'll do reaction of carbonyl compound with electron-rich alkenes. Now, generally what happens, the carbonyl compound absorbs light energy and itself gets excited. That excited state may be in the singlet state or in the triplet state, depending upon the condition. Because sometimes singlet state will go to triplet state by intersystem crossing. Then that particular excited state of carbonyl compound will react with ground state alkene. Remember, ground state alkene to give oxytane. So sometimes that excited state may be singlet, sometimes triplet, or sometimes both the state will be observed. So the product formation of alkene may be one product or maybe more than one product. That means it may be stereoselective or it may not be stereoselective. So first of all, we'll discuss about electron deficient alkene, addition to electron deficient alkene. So see here, reaction pathway varies according to the type of carbonyl compounds and alkenes involved. So depending upon the nature of the carbonyl compound, nature of the alkenes, the reaction path will vary. So reaction path will vary means whether the carbonyl compound will be singlet state or it will go to triplet state by intersystem crossing. It will depend upon the reaction condition and the carbonyl compound and alkene involved. And the next point, addition of simple aliphatic or aromatic ketones to electron-rich alkenes involves attack on ground state alkene by the N2 pi star triplet state of the carbonyl compound, giving rise to all possible isomers of the oxytanes. So generally what happens if we have simple aliphatic and aromatic ketones, that particular ketones after absorbing light gives a transition. What type of transition? It may be from non-bonding N to the anti-bonding pi star orbital. And in the process, first of all, singlet state will form, and that singlet state will come to triplet state by intersystem crossing, because triplet state is more stable than the singlet state. And that particular triplet state of carbonyl compound will give us isomers, different isomers of oxytanes. Means it will react with alkene to give different isomers. And that particular isomers may be obtained because of what? Spin rotation. Okay, spin rotation will take place or spin inversion will take place. Now see here, the reaction is non-concerted because the reactive excited state is a triplet state. See, concerted reaction means a one-step process, and non-concerted means more than one-step process. That means here, excited state, that is triplet state is formed. That means intermediate is formed. Therefore, it is non-concerted reaction. Again, the triplet adduct, the initial adduct of this reaction is a triplet 1,4 diradical, which must undergo spin inversion before product formation is complete. So what happens? The carbonyl compound will be excited to the triplet state and it will form 1,4 diradical. Diradical will form, which will undergo spin inversion and then product formation will take place. Then next, stereospecificity is lost if the intermediate 1,4 diradical undergoes bond rotation faster than the ring closure. Then means if bond rotation is faster, means 1,4 diradical will form, is not it? So if there is a spin rotation, then what happens? If the spin rotation is very fast, then stereospecificity will be lost. And if it is slower, then ring closure will form, then there will be stereospecificity. Remember this particular point. So now let us explain this particular addition to electron rich alkenes by citing examples by this shown in the slide. So here the benzophenone is reacting with this particular isobutene, and we get two products. One is 90% oxyten, another is 10% oxyten. That means one is major product, another is minor product. So what happens is that this particular benzophenone, after absorbing light, first of all gets excited to singlet state. However, this singlet state is not that much stable, therefore it converts to triplet state by intersystem crossing. So this is the excited triplet state structure where we can see that the spin state are parallel. That means this is triplet parallel. Therefore, this particular excited triplet state will react with this ground state alkene, which is isobutene, to give two probable intermediates, two probable diradical, and both the diradicals are in triplet state. Now these two triplet states may spin inversion take place and give you these two products, means these two intermediates. Now these two intermediates individually give bond formation to give us this oxygen in the left side, which is 90%, and on the other side we get oxygen 10%. So one is major product and another is minor product. So here we may say that it is stereo specific because 10% product we can neglect. Now I want to highlight why this is 90%, why it is major product. See here in this particular diradical obtained after intersystem crossing, the diradicals are tertiary free radicals are formed here. This is also tertiary, this is also tertiary. So most stable, tertiary is more stable, being more stable, it gives you the product which is the major product. Whereas on the other side, towards the right side, the particular CH2 with a free radical is primary in nature. Therefore, this is primary in nature, so less stable, the product formation will not be favored much. Therefore, it is 10%. So here, that's why one product is 90%, another product is 10%. Now, see here why it is so. Again, I'm explaining by this slide. So the more energetically stable of the two possible biradicals is formed more readily. So energetically more stable will form more readily. So In the earlier slide, the tertiary free radical is energetically more stable, that's why it is formed more readily. So the major product. Thus, reaction is regioselective reaction. That's why the reaction is one is 90%, another is was 10%. So one is 90% means it is dominating, so it is regioselective reaction. The consideration of biradical stability is certainly applicable to the prediction of the major product of the cycloaddition. So in this kind of addition, cycloaddition, we can predict the major product by looking at the stability or understanding the stability of the biradical form. So, in the next point, the two important rules for the successful synthesis of oxytens have been put forward. So, there are two rules, and always these two rules are followed. Then only the oxygen formation will take place. Number one, what is that? Only carbonyl compound with a low-lying N to pi star state will form oxytens. That means the N to pi star transition must be low lying. That means the gap, energy gap between the non-bonding and anti-bonding pi star must be small. And number two point, the energy of the carbonyl excited state must be less than that of the alkene to prevent energy transfer from the carbonyl excited state to the alkene. So always the energy of carbonyl excited state must be less compared to the ground state alkene. Otherwise, there may be energy transfer. So if energy transfer takes place, then the oxygen product may not be possible. So as far as the addition of aromatic carbonyl compound is concerned, only the triplet state is reactive. Why it is reactive? Because inter-system crossing is very efficient in case of aromatic ketones, and consequently a triplet biradical intermediate is produced. So remember, if we take aromatic carbonyl compound, then the excited state is always the triplet state, and that triplet state is actually obtained by intersystem crossing from singlet state. So remember this particular point. However, in the next point, if instead of aromatic carbonyl compound, if we take aliphatic carbonyl compound, say here we are taking alkyl ketones, the reaction of alkyl ketones has less efficient intersystem crossing, thus permitting reaction of both the singlet and the triplet state. Both singlet and triplet states show equal reactivity for the reaction. The singlet state reaction obtained at high concentration of the alkene. On the other hand, triplet state reaction obtained at low concentration of the alkene. So, if your carbonyl compound is aliphatic, then intersystem crossing does not takes place, but with equal probability. That means both singlet state and triplet state will be observed, and from both the state, product will be formed. Only thing is that with singlet state, we need high concentration of alkene, and with triplet state, we need low concentration of alkene. So there will be no any stereoselective reaction in case of aliphatic ketones. Now here, different case. Now we'll discuss about addition to electron deficient alkene. These are electron deficient case alkene. Earlier we have discussed addition to electron rich alkene. Now what happens to this particular point, electron deficient alkene? Here we have taken alkene which is electron deficient. That means dicyanoethene, where cyano groups are electron withdrawing. So this alkene is electron deficient. So what will happen? Photocycloaddition of aliphatic ketones to electron deficient alkenes, particularly dicyanoethene, involves addition of singlet state excited ketone to ground state alkene. The reaction is stereospecific, and the stereochemistry of the alkene is retained in the product oxytene. So here stereochemistry is retained because this particular dicyanoethane can exist in cis and trans form. Now here we are treating with this particular acetone with cis dicyanoethene. Now the product formation, of course, in presence of UV light, and the product formation will be, or the stereochemistry of the oxygen will be cis. That means if we perform by cis alkene, then our product will be cis. And on the bottom, if we perform this reaction with acetone and trans 1 to dicyanoethene, then the product will be trans oxetine. So depending upon the ethene, means electron deficient ethene, whether it is cis or trans, the product will be cis and trans 2. Now we'll further move to the, yes, yes, yeah, yeah. ইয়াৰ আমি ইলেক্ট্ৰন ডেফিচিয়েণ্ট এলকিন লৈছোঁ। ইয়াত ইলেক্ট্ৰন ডেফিচিয়েণ্ট এলকিন আৰু এচিটনৰ লগত বিক্ৰিয়া হ'লে যদি চিছ ট্ৰান্স এক্সিষ্ট হয়, তাৰমানে ডাইচাইনো ইথিনটো চিছ এণ্ড ট্ৰান্স আমি লিখিব পাৰোঁ। চ' ষ্টিৰিঅ' কেমিষ্ট্ৰি যদি আমি চিছৰ লগত বিক্ৰিয়া হৈছে, প্ৰডাক্ট অক্সিটেন হ'ব চিছ অক্সিটেন। আৰু যদি ট্ৰান্সৰ লগত বিক্ৰিয়া হয় তলৰ ক্ষেত্ৰত, এইটো হ'বগৈ ট্ৰান্স অক্সিটেন। এইটো ইলেক্ট্ৰন ডেফিচিয়েণ্টৰ ক্ষেত্ৰত। গতিকে ষ্টিৰিঅ'স্পেচিফিক প্ৰডাক্টে পোৱা যায়, মানে দুইটা প্ৰডাক্টে নাপায়। সদায় চিছ ল'লে চিছ অক্সিটেন, ট্ৰান্স ল'লে ট্ৰান্স অক্সিটেন। চ' এলকিনটো চিছ লৈছোঁ নে ট্ৰান্স লৈছোঁ তাৰ ওপৰত নিৰ্ভৰ কৰিব। অ'কে, এতিয়া আমি আকৌ Petanovusy reaction in a different case. Let us consider different case. Different case in the sense that oxygen formation with dienes. Etia, if we take dienes, what type of products can be obtained? So here, see here, formation of oxygen occurs from S1 state of the carbonyl compound. Therefore, dienes gives stereospecific reaction with carbonyl compounds. So diene always give stereospecific reaction. So here, supposing you may get this product or you may get product depending upon the mechanism involved. Supposing first product, if we want to get the first product, what type of mechanism will be involved? Like this. So this carbonyl compound, first of all, absorbs light rays and it will be irradiated as singlet state. So excited to singlet state, so there will be free radicals generated. Now these free radicals will combine with this 1,3-butadiene to generate another stabilized free radical. So see here, these free radicals are stabilized. Why stabilized? Because this particular free radical is tertiary free radical, and this free radical is stabilized because of this double bond in conjugation. So therefore, these two stabilized free radicals will combine to give us a cyclic oxygen ring. Now supposing if we want to do the mechanism for the second product, so the formation of second product will be like this. So this particular carbonyl compound will be excited and it will give you a singlet state. This particular singlet state will react with this particular 1,3-butadiene in the fashion as shown in the slide, and you will get this particular uh, biradical. So this particular biradical again combined to give us oxyten. Now tell me, from these two mechanism, actually which will be major, which will be minor? The first product will be major, second product will be minor. Why? Because this particular free radical, that is intermediate, is more stabilized compared to the bottom one. Because in the bottom one, this particular free radical CH2 dot that we have seen is not stabilized and it is primary in nature. That's why the product formation will not be much favorable. However, it is shown that what the product is formed, but one will be major product, another will be minor product. So if you are asked to predict, you have to explain on the basis of this stabilized free radical intermediate. Similarly, the oxygen formation with dienes are these two. Here, this carbonyl compound with this particular six-member diene gives this particular oxygen. Similarly, this carbonyl compound reacts with this particular 8-member diene under photochemical condition, gives cis and trans diene. So this is the oxygen formation with dienes. So carbonyl compound reacts with diene to give us oxytens. Now another example, oxygen formation with alkynes. So even with alkynes, oxygen formation will be there. So carbonyl compounds undergo photochemical cycloaddition reaction to alkynes to give oxytens, which are usually not isolated but isomerizes to alpha beta unsaturated carbonyl compound in a subsequent thermal reaction. So in this particular reaction, on thermal condition or on heating or warming, the oxygen, which is not that much stable, will convert to alpha beta unsaturated carbonyl compound. So in the example, this particular benzaldehyde reacts with this particular alkyne, which is uh, butene, gives oxygen. Now this oxygen on warming or on heating converts to alpha beta unsaturated carbonyl compound. Similarly, if we take benzophenone and we take this particular alkyne having ether group, converts to oxygen, but this oxygen is not that much stable, so easily on warming or heating it converts to alpha beta unsaturated ester. This is the alpha beta unsaturated ester. So like that, oxygen formation takes place with alkynes. Again, let us see about intramolecular Paterno-Bussy reaction. This is the intramolecular Paterno-Bussy reaction. That means the reaction must take place within the same molecule. So since Paterno-Bussy reaction takes place between carbonyl compound and alkene, that means the same molecule must contain C double bond O and C double bond C within the same molecule. So intramolecular Paterno-Bussy reaction is mainly given by gamma delta enons. That means there must be C double bond C at the gamma and delta position. At least there must be C double bond C at the gamma and delta position with respect to carbonyl compound. Because carbonyl compound can be changed to enons. We say enons. Anyway, you must know that only gamma and delta position must have double bond, C double bond C. Now, the efficiency of these reactions can be attributed to the rapid rate of interaction between the excited C double bond O group and the ground C double bond C group. Here also, the light ray is absorbed by carbonyl compound only, and carbonyl compound get excited in the process, and excited carbonyl compound will react with C double bond C to produce oxygen. Okay. The combination of substrates allows the formation of regioisomer. So there are two regions, is not it? C double bond C, but one of the region will be selected. So yields are high and there is usually no byproduct. Means no unwanted product is formed. So product will be high, that's why no byproduct. So this particular reaction is very important and it is very efficient method. Why it is efficient method? Because by applying this particular intramolecular Paterno-Bussy reaction, we may synthesize various organic compounds. Only thing is that depending upon the organic compounds we want to prepare, we have to take respective carbonyl compounds having C double bond O and C double bond C. So see in this particular example, here this is the example where we have taken C double bond O and C double bond C in the same compound. So with respect to this C double bond O, the C double bond C is at gamma delta position because this is alpha carbon, beta carbon, gamma, then delta. Okay, so this particular compound on subjecting to ultraviolet light produces excited compound, carbonyl compound. So C double bond C will be excited to singlet state first of all. So this oxygen has free radical and carbon has free radical. Now, because this particular carbon is already tertiary free radicals and another oxygen is free radical is more reactive compared to the this tertiary free radical. Therefore, this oxygen free radical will combine with CH2 in this patient, and in the process there will be free radical generation at this particular carbon. So the free radical will be now secondary. So in the next step, these two free radicals means this biradical will combine directly to give this particular oxygen. Similarly, in this second example also, we have C double bond O and there are C double bond C bond. Therefore, if the reaction is performed under photochemical condition, first of all, C double bond O group will be excited. So this is the excited state. So now this oxygen lone pair will be attacking the C double bond C in the fashion that the tertiary free radical is generated. This tertiary free radical is generated. So in order to be more stable, this partial, so there are two free radicals generated. One is tertiary free radical, another is secondary free radical. And in the next step, both these free radical will combine directly to give us this particular oxygen. So this is the beauty of oxygen reaction. Similarly, in this particular bicyclic compound, same reaction will follow. So we get these particular free radicals, excited carbonyl compound. So this excited carbonyl compound will react with this C double bond C to give us this particular oxygen ring. One of the most important application of this particular intramolecular pattern-Bussy reaction is the preparation of azulines, which is polynuclear compound. This is a polynuclear compound. This particular polynuclear compound azulene can be prepared by pattern-Bussy reaction. So in order to prepare this particular product azulene, we take this particular carbonyl compound. So that there must be alpha, beta, gamma. At the gamma position, there are C double bond C group. So on photolysis, the C double bond O group will be excited like this. So the generation of secondary free radical and oxygen free radical. Now this oxygen free radical in C double bond C will be reacting to give us this particular free radical. Now we have free radical, this free radical is tertiary, and we have free radical here. So this particular free radical and this free radical will combine to give us this particular oxygen. Now this oxygen ring, when we perform reduction in presence of palladium and alumina, will lead to azulene. So like that, azulene can be prepared by applying pattern-Bussy reaction. So this is all about pattern-Bussy reaction, where we have seen a lot of important organic compounds synthesizing. We have synthesized a lot of important organic compounds by pattern-Bussy reaction. So this much slide I have prepared. Thank you all for patient hearing. So any query?